I believe that people have to learn how their tools work. Electricity is around us all the time. And if you need it or if you use it, you should understand where it comes from, how it's made, and how you're using it. I believe that we have a huge lack in our society where people accept that you throw a switch and the light comes on. There's a lot between the switch and the lamp. And if we all were just a little bit more turned on to what turns on, the light, we could fix light switches in each other's houses. Outlets wouldn't explode from a loose cable. People are just unaware and kind of afraid of electricity. I've been using children's toys and handmade electronics to try and bridge that gap by presenting something that's a little fun, a little anthropomorphically disarming. I want people to interact with something that you wouldn't expect to make a horrible sound or even be that interesting. But as all of you have interacted with these today, it makes crazy sounds. There's all kinds of things to do in electronic devices. There's a lot to learn even in a children's toy. In presentations that I've done with Data Garden out at Bartram's Garden and down at the Magic Gardens on South Street, people have approached me and said, oh, I know how a baby toy works. You just push the button and it makes a sound. There's more to it than that. And understanding the electronic processes in our everyday objects can help us all fix the things we have, make sure we don't buy crapware, and can probably raise the standard of all the devices that are produced around us. How many things do you have? I mean, we all probably have phones in our pockets that when they are broken, they're never going to come back. That's okay. I'll come. I believe that if we know more about the electronics in our everyday lives, we can be more picky consumers and we can demand higher quality devices that can be interfaced with, that can be modified, and that will continue to work. So circuit bending is the term used for modification of small electronic devices. And there's a couple basic tenets to circuit bending if you're interested in modification or if you're interested in making weird sounds that you really should follow. Because electricity is dangerous out of the wall, you don't want to modify something that you plug in. This actually also extends to the world of an amplifier. You don't necessarily want to modify a toy and plug it directly into a big amplifier unless you know what you're doing. Circuit bending is very fun, it's very easy, and you can go through any device that's battery powered and you're not going to hurt yourself. But it's very important to experimentation should only be with a battery device. I've done a lot of work with devices that plug directly into the wall, and let me tell you, it's a lot of stress when people interact with something that plugs in. You actually have to know what's going on with it. But if you have a greeting card that plays a weird note, or if you have a baby toy, open it up, lick your fingers, stick it on the circuit board, and find out what's going on inside that device. Don't be afraid of it, and that's my favorite part about circuit bending. When you take a toy or an instrument and you modify it, it expands your own interaction with it, and it shows that you don't have to be subject to the limited features that someone's offered you on a device. You can find out everything that a device can do. Easter eggs can be found inside of a lot of devices. Most electronics are reused from other components and resourced. Most of my devices are really just based on a simple sample inside, and I re-pitch, I re-clock that sample playback. So I would say most toys that you interface with from like 1983 up to the late 90s are the exact same insides. So just taking apart a few things, you can learn a lot about a big diversity of objects. What I like to show with circuit bending is I want to graph the electrical properties going on inside of a circuit. These are invisible properties. We can talk about the mathematics, or you can draw a schematic, but it's hard to see with your eyes or to experience what's going on inside the circuit. By using a children's toy that makes sound, I try to utilize the sound to graph what's going on inside the object. It's inside a plastic device, it doesn't emit a lot of light, things move very quickly. But for those of you that are playing with the apples, after you interact and interface with the apples for a little while, you can find the ways that you can get an effect, and you can find the ways that you can make an influence on the electronic device. This then gives you a little bit more knowledge about what's going on inside of it, and it can help even reverse engineer a system. So like I said, most of these toys are just basic sample playback units. For For example, everyone's favorite Elmo. Let's see. Okay, turn a little delay down there. Elmo just is a simple baby toy. Makes a handful of sounds, and it has lights. And everyone loves light-up devices. I've added a pitch knob to this device, and what it does is it slows down or speeds up the sample rate of the sample that's being played back. So this isn't something you lay your own sample in, it's just the dumb sounds they've included, which become gradually more and more dynamic. And it can be exciting to see what'll come out of a device once you slow it down really far. I like to utilize devices slowed down 3 or 4 in a row in order to create polyrhythms. Isn't it beautiful? Watch Elmo go indeed. Another thing that I always have to do when I'm modifying devices is add an output, and that really is what makes things fun. Most toys have a speaker built into it, but adding an output to the device makes it so much more dynamic. You can use it with effects like the delay that I've got here. You can plug it into big PA equipment. One thing that's very important to note is these devices contain a speaker, and if you're plugging them into a big PA speaker, microphones and speakers work by the exact same principles of diaphragm vibrating, moving a coil of copper through a magnet, if you've ever taken a speaker apart. So if you plug in a device with a speaker in it to a big PA, it's going to feed back and feed back and feed back. And a lot of circuit benders have that trouble when trying to perform out. It'll sound great at home or just sitting around or in headphones, but once you have a big array, it's hard to actually get it to sound well. So when you're ever going to go into a device, it's important to use a switching jack. So when you plug into it, it turns off the speaker. Another reason that I really like using children's toys is the durability. If you're trying to have 100 people to interact with a device, a custom-made synthesizer, you're going to run into trouble. Parts are lossy, knobs and switches tend to be weak. Even if they're old stock, even if they're good military hardware, it's not the easiest thing, and people are very, very vicious with devices. I love watching people beat up on the children's toys. It'll take a beating and it'll keep on going. The same reason that I use apples for my interface. People can really hang on to the thing, throw it around, even rip it off and plug it back in. Everyone loves plugging the apples in and out. It creates an easier environment to interface with versus bringing a beautiful old synthesizer from home and saying, here everyone, you can play with it. I want all of my devices to be as accessible as possible so other people can not hurt themselves, not hurt it, and not be afraid of it when you're exploring and when you're experimenting with these devices. Another thing that I do with most of my devices is I create patch points. I don't know if you can see the 2 little dots on the side here, or all of the patch points that are on the Apple distortion unit. By having patch points attached, I'm able to experiment with the device further to try to figure out what's the best range for a knob. I use a little button bay that I made. It has buttons on the back and a series of knobs on the front, and patch cables. So I can plug into one of my devices and figure out exactly what the range is before the device crashes. There's nothing like trying to perform with a circuit bent children's toy and having it shut down right in the middle of what you're doing, or turning the pitch or the rate that the clock's moving too high and having the whole unit burn out on you. I have burnt out many, many children's toys. So using an experimenter's bay and patch points allows you to really find the fine range that can be most musically useful, and even define presets that you would want to use. For instance, if you find a certain resistance makes a killer drum sound or a hot bass sound, wire up a resistor to a switch, and then it'll always be exactly at that pitch. It makes it a lot easier to revisit and continue to reproduce things in kind of a chaotic world, if you can't tell that this is a chaotic world. And sound and color is another wonderful point. I wish that I was able to bring my Death Star here, but she suffered a horrible death on the experimenter's knob bay. by having a visual element to these devices, not only just like the pink plastic, but having lights, people really feel like they can be involved with it. And you need to give people multiple levels of feedback. And I think this is why we are relatively unawares of electronics and how electronics work. Because if it's all contained inside a system, you have no idea what's going on. It's trapped inside the box. By having sounds and light, you can really see what your modifications are doing. Some of the hottest circuit bent devices that I've seen on the internet have all kinds of lights that just show and graph a little bit of what's going on inside it, so the performer can try to keep up with the craziness that their devices are putting out. This is a nice shot of the Cookie Monster. I hope some of you have enjoyed playing with him today. And I have the inside shot of Cookie also. I want people to see what's inside these devices, and I want you to go inside the device yourself. There's not much going on here. Just this one circuit board right here is pretty much everything. It's a single black blob, which controls all of those samples. And then the bigger brown board is all the buttons that are tactile on the front. Another device that I didn't bring today is a glorious Transformers voice changer. So I don't know if any of you all had this back in like 1984, but I did. It's an amazing device because it has all solid-state components. When you find a really old device, it's not just going to be some microchip or a black blob in there. You're really going to have transistors and capacitors and a trim pot. It's amazing what you can do inside of there. You can actually reverse engineer that system. You can see what's going on with it. Finding really old children's toys can create an exciting environment so you know what you're doing. It's not just hackery. You can see what your changes are doing, and you can actually see it. I wish that I had a shot of the other side of just the traces on the board on the other side. It's so simple. And when you see how simple something like a crazy voice changer is, especially when it was implemented in the 80s, it makes you wonder why things are so complex now, or why it would be trapped behind a little black blob or inside of a chip. The family favorite yodeling pickle is a very pleasant device. I was gifted this a couple Christmases ago. The yodeling pickle actually is what it says it is. It's a pickle that yodels. So some people interacting with it think that I've added the yodel, but I wish that I had thought of it. What I've done is the same thing I've done to all my devices. I've found the black blob that controls the samples. I found the resistor that controls the rate the samples are played back, and I've added a potentiometer, variable resistor, to start controlling it. The yodeling pickle pitched down sounds god-awful. Pitched up very high, it's just a crazy noise blast. But it's also very stable. So people have enjoyed working with this because you can go from a horrible twill I love the yodeling pickle. It's a great example. It's very portable. It's very accessible on the inside, and it's if you could see just this little circuit board there, the way that you can experiment with that is just lick your fingertip, put it on top, and eventually you'll find the points that when you cross, or when you give a little resistance between them, like my knob that I've added on there, it'll make an effect. It's so easy to explore these devices, especially the further back in time that you go. This is an image of the inside of my Panasonic Tootaloop. A few of you are playing with this. This is a great radio from the early 70s. It's an AM radio. What I did was I added these 3 copper strips to the outside. They're attached to the capacitive controllers in here that actually pick up radio waves. And so what I've done is I use this to really graph radio properties. You've all heard of a theremin and maybe have seen someone interacting with a theremin. A theremin is made up of 2 oscillators. One is the radio, the AM oscillator, which picks up the person interfacing with it. The second oscillator is the tone, the pretty sound, the woo. So there's a control signal and there's a tone. This is just the control signal. Doesn't do it on command. our bodies interact with the radio signals around us, and vice versa. The radio signals around us vibrate through our bodies. Using this simple AM radio, you can graph that interface level. And what I hope to do is, using an output on this, turn this into a control so I can control the voltage or a pitch on one of my other devices. Again, everything is an experiment in progress, and every day that I can play with it or show people it is another experimental level to go at it. Having people interact with it shows me and teaches me a lot of things. Having people play with the Tutor Loop taught me a lot about how to use it. When I first got it, it just made a little pulsing farting sound. I didn't even realize that you could do horrible squeals. And now, of course, whenever I play with it, I try to make the most high-frequency, piercing squeal that I possibly can. Now, we could slowly step through other devices. There's so many variations of the complexity of devices, and as you go from just a standard children's toy that makes a little sound to something more complex, like the original Speak and Spell with the push buttons. I don't know if any of you had one of those. Push buttons are great. You get into much, much more complex systems. Thankfully, circuit benders have well documented the Speak and Read, Speak and Spell, and Speak and Math series. So it's easy to find instructions on how to mount components, where to add components, and the limits that you can actually take these devices. The thing that I have struggled with the Speak and series is the profile. It is so thin, it's jam-packed with stuff, 90% of it's full of batteries. So there's not a lot of places to put stuff. It's really been interesting for me to see what other circuit benders and modifiers do, where they're going to put the knob, where they're going to put the switch. I took that challenge with the Speak and Read, and I began putting all of my components underneath the handle. Just because when I would put a Speak and Spell in my backpack, if there's a bunch of switches on the outside, it switches them on, makes a horrible noise in the bag, people look at me weird on the train. So by trying to put it kind of in a controlled environment, I thought, well, that would be a little bit easier to control the device. And here's a nice shot of just those switches and knobs. The hardest part with interfacing with the Speak and series is that you quickly can crash the machine. And it takes a lot of tuning and searching to find the very few beautiful things that the Speak-ins can do. So just as a quick example here, the Speak and Read has a wonderful garble that it puts out if you tweak it just right. See, unstable. Let's try one more time. He's not a happy camper. Let's see. And actually, he made the point for me. These are very unstable, very difficult devices to perform with. I've tried to perform with a math, a read, and a spell, and the read's normally the one that works. That's why I brought her out tonight. Hopefully at some point, if anyone had heard this earlier when it was just spitting out garble, I'll try to kick it up later on tonight too. But the Speak-ins are fun to modify, they're readily available out there, and they're very well documented, but it's not for the faint of heart. Once you find all your mods that you want to put in it, then you have to put your switches in. So if you're good with the Dremel tool, you're set. And I would suggest, I believe it, I would suggest practicing on more simplistic devices so that you can make other cuts. I've messed up more than one Elmo toy. It sucks when you mess up the case of your Speak-end. So outside of children's toys, there is also simple circuits, and none more important are the simple circuits that were in Forrest Mims' Radio Shack books. Back in the 80s, or maybe even the 70s, Forrest Mims, a wonderful engineer, put out a series of books for experimenters in Radio Shack. What I have here is a stepped tone generator, the Atari Punk console. This is a single chip, the 556, which is 2 timers. By having 2 timers running against each other, you can create square waves, you can create pulses, you can create pulse width modulation. It's a really easy way to start getting into basic electronics. It's very, very well documented. And the funnest part for Atari Punk console for me wasn't just making it, point-to-point soldering. It was trying to figure out how to cram it inside an Atari joystick. I spent many weeks trying different situations, different orientations, different size speakers. When I finally got this particular kit in, it was a lot of hot glue. But she looks really great performing with her bright blue light. At the same time, there's other commercial kits available for the Atari Punk console. GetLoFi.com, an amazing site, great for circuit bending, great resource, lots of different components, produces a circuit board for the Atari Punk console. So I've also done a couple devices where I've used the commercial board, made my own modifications for the sounds that I'm really going for out of it, and it's a little bit more simple to have a sturdy board rather than a point-to-point solder pile with a bunch of hot glue inside the Atari joystick. The main Atari joysticks are really visually appealing, and people know what it is from a distance. They really feel it. But my favorite one, and I should have brought him, was the driving controller. The driver controller is absolutely a spectacular device. When you take apart Atari controllers, they're very, very simple devices on the inside. If you have a Pong set that you don't really play Pong anymore, or you have a driving controller, take it apart. There's a couple really cool encoders in there. So this is before the board was populated, just making sure that all the crap would fit inside of it. So while I was building these Atari Punk consoles, and I did about 6 different joysticks, I thought, I want something that can drive them. And so I took the Atari that I had, and I turned it over, and I made an 8-step sequencer. It's really fun to find basic chips that will do big functions for you. Inside the Atari Punk console sequencer, I put a CD, was it 4017, decade counter, and a tap tempo clock. This allows me to sequence any of my devices that have patch points on them, and using a series of resistance knobs, I was trying to get my Atari Punk 303 going on. It worked really well in very controlled environments. I didn't bring her tonight because it's a lot to set up to actually get something meaningful out of it. But once you plug this thing into the Barbie karaoke machine, serious stuff goes down. All kinds of wonderful tones can be found inside a Barbie karaoke machine, and sometimes having your hands off of the device and letting a machine sequence it for you really can give you a lot of tones and can give you a lot more feel for what's going on inside the machines. So I just talked a bunch about electronic devices, children's toys, and then moving through slightly more complex devices and even making your own. Now I'm going to touch upon a lot more complex machines. Everyone's got broken distortion pedals, delay pedals. Musicians kick, beat, destroy their equipment. It breaks my heart. But as a modifier and a repairist, I'm very happy to interface with devices. The trouble is the relative complexity. Even after playing with all of these toys, there's a lot going on in this little tiny package. This is a Gaia-tone delay. Honestly, they're much smaller than just even this bag. Ridiculously tiny thing. The knob on the top right-hand side broke off, and so I attempted to fix it. These devices are made to be broken. It's so small, it's so tight in there. There's no way that you could find out how you could fix it. And if you even went in, or when I went in, it was weeks before I figured out what needed to be fixed, and then I gave up. When you get into a really complex device, you may be able to reap components out of it, but it's much harder to actually get it to do anything. Never fear, you can always try, but again, make sure it doesn't plug into the wall before you mess with it. Pedals are great fun, and especially when you have a broken pedal. My very good friend Norman had an original Big Muff, and all of the knobs were broken off of it, the input was broken, and the power leads were broken on the battery. There's a lot of modifications online for Big Muffs, so I added all of them that I could find. So I added 16 modifications to this thing. It is spectacular. The sweetest tone, the cleanest true bypass. The best part about this Big Muff mod, and if you have a Big Muff at home, the one mod that I would suggest is a noise floor. If you've ever played a distortion pedal on a guitar and you're not playing anything, it makes a horrible and then you play the guitar and you get the righteous, crisp grind tone, and then again. A noise floor, or a noise limiter, will cut down on that. And so that's the big knob here. I mean, this is the honey mod out of the Big Muff. So if you're modifying a pedal, if you have a Big Muff, go for the noise floor mod. Even not doing anything else to the pedal will make it a whole new device for vocal processing, which you never could do with a distortion pedal cranked up, or for high-end fuzz bass, where it's just and then gone, very clean. Big muffs are a wonderful toy to mess with, and they're big, so there's enough room to actually manipulate stuff inside. So this brings me to the Casio SK series. I didn't bring an SK with me tonight, but they are a wonderful machine to develop in. There's so many modifications in the SK1 and the SK5, and if you're really savvy, you might find an SK8 or an SK10. Here in this image is, a small pile of Barbie karaoke machines, a new Casio SK5, and then my old Casio SK5 that I'm cannibalizing for parts. One of the key things to do in one of these SKs is the same kind of pitch effect that I was doing on the children's toy. You want to try to pitch down that Casio keyboard. You can get serious bass. I use, from getlofi.com, the LTC Precision Oscillator, which is the little tiny circuit board right there. This takes over the clock and drives the entire system slower. By slowing down the system, it plays the samples at a slower rate and makes the pitch lower. The beats that come out of this thing are banging, and when you pitch it down and slow it down, you can get really dirty grooves. And I can even attach that to the sequencer and modulate how it pitches itself down. There are so many bends inside of the SK series, it's hard to pick which ones you want to do. And again, just like the Speakin' series, there is very limited room on the inside. So what I've begun to do is practice using a patch bay. So when I circuit bend, I find all the points that I want to modify, and then I get a 25-pin D sub-connector, and I mount everything to that sub-connector. That way, everything that I'm modifying on the inside can just go through one box and actually rock out. One of the cool things about the Casios is the way that they program themselves. When you hit a button on a Casio to play a sound, not necessarily a note key, but playing a preset, it sends all the data from the memory into the CPU. Then you can play your piano sound. By using the modifications, while it's loading that program, you can actually have a stable circuit bent sound. And this is one of the reasons that the Casio SK1, I think, is one of the most celebrated circuit bent devices, because it can actually be stable. But how do you find one of those bends even after you get a bunch of points? How can you find something that's actually worthwhile? Well, I built an elaborate breakout bay in order to try and find what points, what resistances, what controls make the best sounds, the best presets. And I've worked with a series of bands where I would craft a sound, pick it out on this device, and then build another breakout module, such as a 25-button matrix, in order to make it more performable, more playable. This is a really fun way of interfacing with the Casios. It's 25 buttons. Each button's attached to one of the pins that come out the back, and it's all momentary, so you can hold down a chord of buttons and find a weird series of patches that you can cross together. Things start getting more and more difficult as we modify electronics. This is a little shot of the inside of a QY8. This is a Yamaha 4-part MIDI sequencer that I tried to modify. Using the same technique I did on the SK, I found a series of patch points to add to the chip, and I began to break them out to a D25 sub-connector. The hardest part with modifying something like this, besides the risk of completely destroying it, is bridging the pins. When you're soldering on something that's smaller than your thumbnail, it's very easy to leave solder traces behind. This is where practice comes in. This is where having an already broken device that you play with your soldering iron on really can help. And this is also where I felt I was proving to myself that I was able to rework and modify something with surface mount components. And here's a little shot of the QI8 lined up to the patch bay. The QI8 is a really dynamic sequencer. It's a basic MIDI sound bank, and by modifying the sounds that it's sequencing, you can have a really, really strong circuit bed sound with a very nice sequence. Hopefully next time I come out to 8static, I'll bring him all programmed up. This is a shot of a DR202. I love groove boxes. I always liked having a multi-part sequencing drum machine, especially when it had like hardcore synth parts in it. The DR202 is a dirty, dirty box made for grinds and grooves. It's made for remixing, and the sound set is pretty righteous as it is. It has huge bass. Well, what do you get when you circuit bend huge bass? Well, you get even more huge bass and crazy warbles and speaker blowing noise. Again, I broke this out with 25 wires to a 25-pin patch bay, and he's not plugged into the patch bay there, but you can see the 25-pin sub-connector. This makes it so much easier to find modifications, pick out what's worth keeping, and make a custom box that you can use with the device. So I have a Barbie karaoke problem. I was introduced to the Barbie karaoke machine about 7 years ago, and they are one of the most dynamic circuit-bendable devices that I've found. It's got a cassette, which you can use a loop cassette, or you can slow the cassette down, or you can speed the cassette up. That's fun in itself. But it also has an echo delay circuit. This is an analog bucket brigade delay. It's the same thing found in really sexy boutique delay pedals. By reverse engineering and playing with the insides of a Barbie karaoke machine, you can learn about electronics for both the delay chips and powering motors, managing electricity in a system, and also trying to find where to put components. It seems like there's a lot of space inside these boxes since there's a speaker bays, but it's really, really kind of tight in there. Trying to find a way to actually wire it all up becomes a bird's nest very, very quickly. I've done a bunch of these Barbie karaoke machines, and each one has its own personality and each one has its own style. I've tried to do patch points on a lot of them in order to have them interact with each other and to be sequenced. The latest device I have, and this is in build of number 4, doesn't really have that many patch points. I tried to make it as clean as possible and as usable as possible. The Barbie karaoke machines are not easy to use, but they're easy to modify. They're easy to learn what's going on inside of it. And as well, they're very well documented. A wonderful circuit bender and educator, Peter Edwards of Casper Electronics, has tons of information on casperelectronics.com for how to modify Barbie karaoke machines. If I found his site the day that I started, it would have saved me a lot of time, but I wouldn't have learned nearly as much through the experimentation that I did. But I can always say, when in doubt, hit CasperElectronics.com, and he will be able to inspire you through many devices, including the Barbie karaoke machines. A wonderful event that I try to perform is called Ken, which is my Barbie karaoke lifestyle. Well, I'll have all 4 of the Barbie karaoke machines with 4 artists surround an audience and let them have it. All right, now we're winding down, and we're reaching into really my most contemporary project and something that excites me a whole lot. It is the Apple distortion. This is based on a very simple component, the LM709 operational amplifier, which you can see it's the metal can sitting right there. These were used as op amps in military surplus, and a company called Stein produced a thing called a Crackle box, which is a 6-touch point noisemaker. The Apple distortion I built in order to satisfy a friend of mine who wanted to run his guitar through an Apple. By plugging the guitar directly into the Apple and directly into the amplifier, nothing actually happened, much to his dismay. This is version 3 now with the Apples. I use the same patch point methodology that I do on all my other devices, which makes it a lot easier to test this thing and also how to program it up so it's a usable and interactable device. You can run signals through it, or as we've got in this demonstration here, it's all standalone. But the real power of the Apples is when you have a whole lot of them, a whole lot of friends, and a whole lot of signal going through it. The Apple distortion acts as a distortion, it acts as a filter, it acts as an amplifier, it acts as a radio wave cruncher. I've only begun to touch upon, in my experiments, what this can do. And I believe that by graphing the electrical properties inside a circuit and creating an audible interaction we can learn about what's going on inside the devices, and we can learn about how our interactions with an electronic device produce outputs. Well, I want to thank everybody for hanging out and listening to the wonderful lecture that I've given you. I want to thank everyone for hanging out before this lecture and playing with the devices, because that's really what it's all about. To learn how your devices work, you have to actually touch them, and you have to reach out and find what's interesting to you. So please, learn how your tools work. If any of you are interested in playing with any of the devices, I'm going to keep them up until they kick me out. And I try to do this as often as possible. I'd love to do kids' parties, small shows, large events. The best part of circuit bending is when the public interacts with the device. It's not necessarily the circuit bender keeping it to themselves. It's trying to show everyone that there is magic in all of our daily devices. Thank you all very, very much. Cheers.